So when we're looking at any element, let's take carbon, for example. Okay. Carbon, for example, we know that carbon is 1s2, 2s2, 2p2. Okay. Well, where did we come up with this electron configuration? Well, let's take a look at carbon's, called the Bohr model of the atom, sort of that traditional solar system model of the atom. We know that carbon has 6 protons in its nucleus. Those 6 protons are pulling on the outer electrons in carbon. So we know that carbon has 2 energy levels. 2 energy levels. Okay. And we know in that first energy level, we have 2 electrons. Okay. So that's those 1s2 electrons. And we know in the second energy level, we have 2 electrons, 2s2 electrons, and we have 2p electrons, 2p2 electrons. So if we shoot this thing here with energy, so let's say we pop it with some energy. The first electrons to pop off are going to be these 2 electrons, okay, because they're on the outer energy level, and they are actually in a larger orbital than that s orbital. Okay, so it's going to take a certain amount of energy to pop those off, okay, and that energy is going to be denoted by a peak, okay, on the spectra machine. So that peak is going to represent pulling off these 2 electrons. Okay. If you hit it with some more energy, the next electrons you're going to hit off are these 2s2. Now, it's going to require a little bit more energy to knock off those 2s2 electrons because now they are closer to the pull of this nucleus right here. Notice the nucleus is really pulling in on all of these. Okay. It's pulling in the most on those 1s2 electrons because they're the closest to the nucleus. Okay. So we're going to have 2 more electrons here, and these 2 more electrons are going to have a little bit more energy. Okay, let's say that this here is increasing energy, and oftentimes we refer to this as the binding energy, similar to the ionization energy that we studied earlier. We call it the binding energy because these electrons are bound to the nucleus. Okay, so we got rid of those, we got rid of those. Now, if we hit it with even some more energy, the last electrons we're going to pull off are these electrons, these 1s2 electrons. So we're pulling off 2 electrons. So it's going to have the same height peak in the spectra, but it's just going to require more energy. So we notice that they're all the same height because we're pulling off 2 electrons in each case. Okay. But the energy for pulling off those 1s2 electrons was a little bit higher because it was closer to the nucleus than those 2s2 electrons, which were closer to the nucleus than these 2p2 electrons. So if I looked at something that had 3 peaks like this, I would know that it's carbon right away. And this is how we can tell what element we are dealing with. We see machines like this anytime we're looking to decode an element. This spectra came before this. We developed this from this. It's also important to know that the height of this peak is relative to the height of this peak. Okay? So whatever you have on this axis, it doesn't mean you have exactly that many electrons. Okay? We know this is 2 because it's the same height as this. Okay? Let's do another example. Let's say we had something like fluorine. We know that fluorine is 1s2, 2s2, 2p5. So we know that fluorine has 5, 6, 7, 8, 9 protons in its nucleus. So if we look at the nucleus, there's 9. Okay, we got that first energy level. There's those 1s2 electrons in it. We have that second energy level. We have 2s2 electrons, and we have 2p5 electrons. When we draw this axis here, we can call this binding energy. We can make this high, we can make this low. The first electrons to get popped off are going to be these p5 electrons. It's going to be very low energy. So we know that this peak now is your 2p5 peak. Okay, it's the lowest energy level. So everything's going to be relative to it. The next electrons to get popped off are those 2s2. So this is going to be a little less than half of that 2s2, and the last electrons get popped off, or that is that 1s2 peak. Usually here we use a slash to indicate that we're moving from one energy level to the other energy level. So when I look at this, this initial part is your 1s2, 2s2, and there's your 2p5. Now let's compare two here. What if we had something like N versus Ne? Okay, and we want to do them both on the same axis. So this is the relative number of electrons, and this is the binding energy. This is high, this is low. So these are things that are closer to the nucleus. These are things that are far away from the nucleus. I'm going to start off by doing the electron configuration for both of these. First, 1s2, 2s2, 2p3, 1s2, 2s2, 2p6. So the first question we always have to ask ourselves is which one of these has a higher binding energy? Another way of saying it is which one has a higher ionization energy? Another way of saying it is in which element is it harder to remove the electrons? Well, if we remember, these are in a horizontal row on the periodic table. They are both in the second energy level. That is to say, the last electrons are in the second energy level. But neon has 10 electrons pulling on its second energy level, whereas sodium has only 7 protons pulling on its second energy level, neon 10 protons. So neon has a higher binding energy. So that means when you pull off neon's electrons, it's going to require more energy. So let's go ahead and draw neon first then. So neon is you're going to pull off those 2p6 electrons first, okay? And then those 2s2 electrons are going to come off there. So this is 2p6, this is 2s2, and then you're going to pull off those 1s2 electrons. I like to draw it backwards because that's the order that they are actually getting pulled off. Now, nitrogen, when you pull off its electrons, it's going to look very similar, but it's going to be overall easier to pull off nitrogen's electrons. Easier because it's only got 7 protons pulling. So nitrogen, again, is going to end with its 2p3. Now that 2p3 is only going to be a little bit higher than that 2s2. Okay, and it's got now a 2s2. It's going to be the same height as this 2s2. Okay, but it's going to be easier to pull those off, and the same height as this 1s2. So notice, the 1s2 and the 2s2 are the same height, but because nitrogen has a lower ionization energy, it's shifted over to the left. So this being nitrogen, and the other one